This is also a really good time to talk about another topic that's closely related to everything that we're saying, and that's to talk about the percent composition of a compound. So we define the percent composition we define this as the percent by mass of each element in a compound. Okay, and we can actually there is actually an equation that we can write to help us determine the percent composition. So the way that we do that, the way we calculate the percent composition is that we take the number of moles of the element, which we represent as N, times the molecular weight of the element, and then we divide that by the molecular weight of the compound. And then we multiply that all by 100%. Okay, so again, N in this equation, N is going to be the number of moles of each element. Okay, so yeah, we can calculate the percent composition. Now, typically, however, what you're going to be doing is given a problem that starts with the percent, and you've moved to find something called the empirical formula of that compound. Okay, the empirical formula of a compound, the way that we define this, the empirical formula, this is the lowest whole numbers that's possible for that compound. Let me give you an example. So the molecular formula for glucose, sugar, is C6H12O6. Okay. And so that's its molecular formula. Okay. If I wanted to find its empirical formula, is there a way to reduce these all down to a number that's not divisible? Absolutely. We can divide all these numbers by 6. And if I do that, we get CH2O. And so this is called its empirical formula. All right. So we can find an empirical formula by using this process that we're going to talk about. It's a 5-step process. So here it is. The first step is that we assume that you have 100 grams of material. Okay. The reason why you want to assume that you have 100 grams of material is that all your percentages are automatically converted to grams. That's why we like 100 grams. All the percentages are automatically converted to grams. You don't have to do any math. All right. The second step is this: convert the grams of the element to moles of the element. And then, third step, we divide all the moles of elements by the lowest number of moles. And what we're trying to do is something called normalization. By doing this normalization, at least one of your numbers is going to be out of 1. So that's the normalizing. Okay. Now, what if, when you take a look at your numbers, you have a number that's like 0.1 or 0.9. Okay. All right. If it's 0.1, you're going to round down to the nearest whole number. If it's 0.9, you round up to the nearest whole number. So if you have a number that ends in 0.1 or 0.9, you round to the nearest whole number. Round up or down to the nearest whole number. If it's anything else, we can't do that. So if it's any other thing, any other number like 0.2 or 0.33 or 0.5 or 0.7, this doesn't work. So if it's anything else, you'll have to multiply by the lowest integer possible to get a whole number. Now, not only will you multiply that one element, but you have to multiply all the elements. So you'll have to multiply all elements by the lowest integer possible. So that way, all elements have a whole number. So let's try a problem out. Here's our next problem. Determine the empirical formula of a compound having the following percent composition by mass. You have potassium, which is 24.75%, manganese, which is 34.77%, and then oxygen, 40.51%. All right, so let's follow our rules. So the first rule is that we assume that we have 100 grams of material. So what I'm going to do is write out each of our elements. So we have K, we have Mn, and then we have O. And for K, we have 24.75%, so that's 24.75 grams. Manganese, 34.77. Let me erase that decimal point. Oops. All right, 34.77 grams. And then oxygen is at 40.51, so that's 40.51 grams. All right, so the next step, we convert all these grams to moles. All right, so for 1 mole of potassium, we put the potassium, 1 mole of potassium on the top, so that way we put the mass on the bottom. So the mass of potassium, according to the periodic table, is 39.10 grams. We're going to do the same thing for manganese. Put the mole of manganese on top. The molar mass goes on the bottom, so that's 54.94 grams. Again, I'm getting that right from the periodic table. And then oxygen, for 1 mole of oxygen, according to the periodic table, it's 16 grams. All right. All right, so if I do the math, K should come out to be 0.63299. Manganese should be 0.63751. And then oxygen is 2.531875. This is really, really, really important. Do not round when you're doing this problem right now. If you round these numbers up, it's going to throw off all of your work for later, for the latter half. So do not round. All right, so looking at these numbers, potassium, K, is the smallest. So what we're going to do is divide each of these numbers by the number that we got for potassium, 0.63299. Now, potassium and manganese are actually really close to each other. So that number for manganese is going to be pretty close to 1. Okay, so the number, let's see, if I get for oxygen 2.53 divided by 0.63299. All right, so the number for potassium is going to be 1. If you do 0.63751 divided by 0.63299, it's going to be really, really close to 1. It's going to be something like 1.007, something like that. All right, but the number for oxygen, if you divide these two, 2.5318 divided by 0.63299, this comes out to roughly 4. And so what's really nice is that we get whole numbers right away. So based on what we've seen, the empirical formula that we're getting is KMNO4. And there it is. Now, what's really nice about this compound is that this is also its molecular formula. Okay. And so that's how you handle a percent composition problem in Gen Chem.